Today we are going to see combination logic circuit part 2, which covers binary parallel adder, look ahead carry, magnitude comparator, decoder, encoder, multiplexer and demultiplexer. This is your next unit. And in today's class I'm going to take about 4-bit parallel adder, 4-bit parallel adder, that is binary adder, and then I'll go ahead with magnitude comparator. So 4-bit binary parallel adder or 4-bit parallel adder can be done by using 74HC283 IC. Okay, if you LT Spice, you can use this IC and you can check how it is being added parallelly. How you are adding two 4-bit numbers. Say for example, if I need to add 0110 and 1001, okay, 1001, I repeat, this is unit number 4. Okay, from the beginning, this is the syllabus for unit number 4, combinational logic circuit, binary parallel adder, look ahead carry, magnitude comparator, decoder, encoder, multiplexer and demultiplexer are the topics that is to be covered in combinational logic circuit part 2, which is under unit 4. Okay, so 4-bit parallel adder, the first topic we are going to see, we are going to add 4 binary bits. State for example 0110 and 1001. So the result is 1111. Okay, instead if I want to add two number, so 0111 and 1011. Okay, see here 110 and carry 1, 111 1 and carry 1, 110 and carry 1, 110 and carry 1. So when I'm adding 4-bit number, I'm resulting with 5 bits, namely 10010. Okay, so this will be carry out. Okay, and this is your output bit. Okay, this is your output bit, and this is your A and this is your B. So A is nothing but A0, A1, A2, A2, A3, 4 bits. Similarly, B0, B1, B2, B3, 4 bits we are going to add. Okay, and if you add A0 and V0, okay, I'm having a carry here. This will be going here. Okay, this has to be moved, carried forward to the next higher significant bit, namely A1, 1 1 1. So this is 1 and 1. Like this you need to go ahead with carry, look ahead with carry. You have to carry your carry to the most significant bits, and you have to get your correct results. Okay, so see here, this is 74HC 283 IC. You can use 74HC 283 IC for getting. A and B is your input, C out is your carry. Okay, this is C in, or C, that will be represented as C, that is your output. Okay, so come here, see, look here, or I should not say this as C, let me take it as your result R. Okay, result R, and these are nothing but you will be having 4 carry in. Carry in is nothing but your look ahead carry, or you're taking your carry forward, namely C in 0, C in 1, C in 2 and C in 3. Okay. So C in 0 for this case, your C in 0 is, there is no carry, so this is 0. Whereas C in 1, I have 1 and I have 1 over here and I have 1 over here. Okay, in all the case I have a carry. Okay, and the final carry is your C out that will appear here in this pin. Okay, so I don't have any carry in the least significant bit. I have a carry in the first position, so that is 1. I have a carry in the second position too, so this is 1. I have a carry in the third position also, so that is also 1. I have carry out in the final position, this is fourth position, this will be in C out, this will be in C out. So 1 1 1 and 0, 1 1 1 and 0. This is how you need to give the input, this is how you need to give the input in terms of IC74HC283. So in terms of logic diagram or the circuit diagram, see here you have each and every bit. So this is nothing but I have said already here. Okay. So 0 triple 1 1 0 1 1 we have added, right? So 0 0 triple 1 1 0 1 1 we have added. So this is 0 1 1 1 0 1 0 1. Okay. So this is A0, A1, A2, A3. Okay, and this is B3, B2, B1 and B0, whereas this is summation 3, summation 2, summation 1 and summation 0. Okay, summation 0. Keep in mind this is the least significant bit. This is 0, 1, 2, 3. Okay, whereas this one whereas this one is your C3 or C in 3, C in 2, C in 1 and C in 0. Okay, whereas this one is your carry out. Okay, this is your carry out. So keep this here. So each bit, this is your summation 0, 1 plus 1 0. This is your summation 0. I am starting from the least significant bit. See, I have a carry in, which is nothing but C in 0. This is C in 1. This is C in 2. This is C in 3. Okay, this is C in 3. So A, B. So this is, I can say this is A naught, B naught. And then this is A1, B1. This is A1. This is B1, A1, B2, A2, and then this is B3, A3. Okay. Similarly, your summation bits here is summation 0, summation 1, summation 2, and summation 3. Okay. So this is your C in 1. As I said, this is your C in 1, which will be your input for the next subsequent bit. Next subsequent most significant bit. And this is C in 2. This is C in 3. Okay. C in 1, C in 2, and C in 3. C in 1, C in 2, C in 3. Okay. For us, according to the example, okay, we know what is A naught and B naught is 1 1. A naught and B naught is 1 and 1. This is 1 and 1, whereas this is 0. sum is 0 and carry is 1. Okay, and then 1 1 1. So 1 1 1, and this is 1 again. Okay, this is 1 again, whereas A2 is 1 0. A2 is 1 0. So 1 0 1 again, 0 and 1 here. Okay, and A3 is 0 1 0 1. Okay, 0 1 and 1 here. So it is 0 and 1 here. This is your carry out. Okay, so your result is 1 followed by 0 0 1 0. This is your result. This is your 4-bit parallel adder with look ahead carry. Okay, next is your magnitude comparator. So what is magnitude comparator? Magnitude comparator compares two bits here. Okay, compares two bits, namely A B. First let me take two examples. Let me take two bits A and B. Okay, so these two bits it will compare and tell us which bit is greater or which bit is lesser, or both the bits are equal. Okay, so you have single bit comparator. The first case we can go ahead with single bit comparator. So A can take one bit 0. So we are comparing only single bits of A and B. So we'll be having four different combinations. 2 power 2 is 4, 0 0 0 1 1 0 and 1 1. What is your output? Either you can have three possible outputs: A greater than B, A less than B, and A equal to B. These are the three possible cases. See here in A and B, both the bits are equal. So this will be 1 output function. This will be 1. And here also A and B both are equal. The output function is 1. Okay. Here your output has to be 0 for this case, and this case two zeros will be there. And here come to the next case, A is lesser than B. So for the second case, this is 1, the rest all are 0. And for the third case, A is greater than A is 1, whereas B is 0. This is 1 and this is all 0. So these are all the possible output functions. Where the function A greater than B is given here. Okay, and A less than B is given here, and A equal to B is given here. These are said to be the three output functions. F3, F2, F1. Okay, so if we do K-map, if we are going ahead with K-map, so input is 2. So 2 means 4 combinations of input you'll be having. For implementing this in K-map, like this you will be drawing the K-map A and B, 0 1 0 1. So we know that 0 0 is 0, 0 1 is 1, 1 0 is 2, and this is 3. Okay, like that we need 3 K-maps for 3 output functions F1, F2 and F3. Okay, whereas the 3 functions are A greater than B, A less than B, and A equal to B. Okay, this is a block diagram of an n-bit comparator. I have taken, instead of n bit, I have taken 1 bit. Okay, the general block diagram is given here for you. So see here, this is a 1-bit comparator. As I said earlier, I have drawn already the K-map function or truth table I have given in the previous slide itself. Here, this is the K-map. Okay, so see, look ahead with the first column. Look ahead the first column here. So you have only 1 1 here. Whereas in the second column, you have 2 1s, and in the third column, you have only 1 1s. So 1 1s, second column 2 1s, and the third column only 1 1. Nowhere you can combine. I have to write as such only. So this is, I am taking it as A naught B naught. So A naught B naught, and this is A naught B naught bar and A B naught. If you look at this one, this is nothing but your XNOR gate. This is nothing but your XNOR gate, and the complement of XOR. Okay, so A XOR B, the complement is your XNOR. Okay, and then this is your A not B not bar. Okay, so we know the logical expression. Now we can implement by using logic gates. Okay, so implement by using logic gates. This and all you know how to implement. I have implemented using the basic gates. This is by using your basic logic gates, namely AND, OR, and not, and this is I have used here x not gate. Okay, for this expression I have used x not, and this can also be done by using your and the or gate. That is what I have tried here, and here this is your using your x nor gate. This is using your x nor gate. Let me go ahead with the 2-bit magnitude comparator. So 2-bit magnitude comparator means again you are going to take same numbers A and B, but A will have 2 bits, namely um, A naught and A1, and I should go ahead like this. A will be taking two numbers, 2 bits, so A naught and A1, and similarly B1 and B naught, B1 and B naught. So you have 4 bits now. Now you have 4 input bits. So 2 power 4, 16 input combinations you have. 16 input combinations you will be having. First develop the truth table. First develop your truth table. First let me go ahead with the truth table. So it can take 4 different, the 16 combinations, you know, 4-bit input means from all 0 to all 1. All 0 to all 1. So what, let us compare here. So it is easy. First compare A1 and B1 and A0 and B0. Okay. So if I'm taking, let me take for example, this is A1 and A0, and this is B1 and B0. Okay. So for the first case, let me take this is 1 0 and this is 0 and 1. Okay, the numbers I'm taking. So first always start from the most significant bit comparison. See if A1 is greater than B1, if A1 is greater than B1. So what is this 1 0? 1 0 is equivalent decimal is 2. 1 0 equivalent decimal is 2. Whereas 0 1 equivalent decimal is 1. So you are comparing two, generally A and B, A greater than B, 2 obviously greater than 1. So this can be easily done by comparing only your A1 and the B1 bit, by comparing only the A1 and the B1 bit. If A1 is greater than B1, obviously and definitely your A will be greater than B, because this is 2, the most significant bit. This is greater than this B, this is 0, because this decides which number is greater. Okay, this decides which number is greater. So obviously A is greater than B, 2 is greater than 1, and hence A is B greater than B. So compare first with your A1 and B1. So see here A1 and B1, if you compare these two number, first A1 B1 both are 0, so this comes under equality. A1 B1 is equal to 0, and this is again equal. So see here, this is equal, A1 and B1, and this is also equal. A1 B1. Okay, so 0 0 0 and 0 0 0 1. Okay, so compare both the bits. See, A1 equal to B1, A0 equal to B0. So when you compare, all the 4 bits are equal, so equality is 1. Okay, so compare here first A1 compare with B1, first bit is equal. For the second case 2, A1 and B1 is equal, and then go ahead with the next least significant bit. So A0 and B0, if you compare A0 and B0, B0 is greater. Okay, B naught is greater. Obviously, your B input is greater. So, A less than B, this is 1. I think you are getting me. First compare A1 and B1. Okay, check for if A1 is greater than B1, it is obvious that check whether A1 is greater than B1. So, if A1 is greater than B1, definitely your A number is greater. And if A1 is less than B1, definitely your B number is greater. And the third condition is A1 equal to B1. If A1 is equal to B1, you have to go ahead with A0, compare your A0 and B0. Here also you need the three cases. Check whether A0 is greater than B0. If A0 is greater than B0, definitely this is your third case. This is first case, this is second case, and this is third case. Third case, A0 and A0 and B0. You need to compare A0 and B0. So check for again the three cases. If A0 is greater than B0, again your A is greater. And if A0 is less than B0, again your B is greater. And check if A0 is equal to B0 again. Okay, if A0 is B0, if both are equal, and we can say that A equal to B. So this is how you need to rule this. This is how you need to rule this out. So like this, fill up the truth table for the following output functions F1, F2, F3. So you need three truth table with four input combinations. So this is the truth table for the four 2-bit comparator. So 4 cross 4 already I have combined and kept. Okay, already I have combined and kept. This is the truth table. This and all you try by yourself. And after this is the logical expression for A greater than B, A equal to B, and A less than B. Okay. Implement this by using your logic gate. Implement this by using your logic. Okay. This is the logic diagram. This is the logic diagram for 2-bit comparator. Okay. For the 2-bit comparator. Okay. 2-bit comparator. You have four inputs A1, A0, B1 and B0. B1 and B0. Okay. So let me go ahead with 4-bit comparator. Okay. 4-bit comparator in the sense we have 4 bits of A and B. So A will be having A0, A1, A2 and A3. Similarly, B will be having B3, B2, B1 and B0. Again, in the same way, you just combine. First, start with the most significant bit. Okay. See, this is 2 power 8, 256 combinations. 2 power 8. 2 power 8. This is 256 combinations. That big truth table is if making that big truth table is complicated. So use some you derive or simplify it logically. Okay. So first step, most significant bit. If A3 is greater than B3, check for A3 greater than B3. If A3 is greater than B3, definitely the number A is greater. Okay. Or if B3 is greater than A3, definitely the number B is greater. Okay. So first two condition, A3 is greater than B3, definitely A greater than B. If B3 is greater than A3, definitely B greater than B. And if both are equal, I have to go ahead with the next classification. The next least significant bit, which is nothing but your A to B2. So if A3 equal to B3, you need to compare either A2 greater than B2. If A2 is again greater than B2, then again which number is greater? A is greater, because already these two bits are equal. A3, B3 is equal. So A2 greater than B2 means A is greater, so A greater than B. For the other case, A2 less than B2, definitely B is greater, so this is 1. Okay, the third case is A3 equal to B3, A2 equal to B2. Okay, and then we need to go ahead with the next comparison, A1 and B1. So again, A1 greater than B1, A1 less than B1, A1 equal to B1. Okay, and if this is also ruled, and I have to compare with A0, B0. A0 greater than B0, A0 less than B0, A0 equal to B0. Fill up the truth table function. Fill up the function. Okay. So implementing this, you can derive, you use your directly from the this expression by Boolean law, by using Boolean law. This can be simplified, and this is equal to expression, this is greater expression, this is logical expression. This is your logical expression. You can implement by using your logic gates. You can implement by using your logic gates. Otherwise, you can use your uh, you can use the device 74HC85. 74HC85. Please hold. I'll share one more Yeah. Is your 74HC85. See here, you are giving for data inputs for, it's a 16 pin IC. It's a 16 pin IC. So you will be giving 4 bits here, 4 bits here, and outputs you will be having three outputs, namely greater than A greater than B, A less than B, and A equal to B. And cascading inputs, for example, why we are going ahead with cascading inputs is, if I need to add a more than 4 bits, namely 5 bit or 6 bit or 8 bit, like that, I need one more IC, one more IC. In that case, from this from the previous IC or from this IC, you need to give it to the next IC, like that. You're getting me? And that I'll tell you in the next subsequent thing. So this is a 16 pin IC. This is your VCC. This is your ground. You have four inputs B, four input A, and three outputs O, and three cascading inputs I A less than B, I A equal to B, I greater than. This is your logic diagram, as I already said. See, compared to this at 7485, so you have this up to this combinations. A greater than B, A less than B, and A equal to B, A2 equal to B2, A1 equal to B1, A naught less than B naught. The next category is if all the bits are equal. Okay, these are the cascading inputs I have said. If you are using a single IC, this is don't care condition. X represents your don't care conditions, and this is your logical output. And if this is equality conditions, if for checking if both the bits are equal, you need to give the cascading input one A greater than B input to be high, other two will be low, or low, high, and low. These are the possible input combinations of your cascading input. Cascading input. This is your 4-bit comparator. See, look here, if I'm using it as a single 4-bit comparator, I'll be giving 4 inputs of A here. I'll be giving 4 inputs of B here. I'll be taking the outputs here. Cascading input A greater than B, A less than B, I have to ground, and A equal to B, I have to give 5 volts. I have to give 5 volts. If I need to compare 8 bits, namely A0, A1, A2, A3, A4, A5, A6, A7. Similarly, B0, B1, B2, B3, B4, B5, B6, B7. So 8 bits, I'll be using 274HC85. So the lower bits in one comparator, the higher bits in another comparator. See here, this is the first stage. In the first stage, I have grounded A greater than B, A less than B, and this I have given 5 volt regarding your cascading input. And the outputs and the corresponding A equal to B has to given to the cascading input A equal to B, and the output A less than B has to be given to A less than B, and the output A greater than B, I have to A greater than B, I have to give to A greater than B, and this is your higher order bits. Here you will be getting 8-bit output comparison. Okay, 8-bit output comparison. This is how you need to compare 8 bits. Okay, this is how you need to compare 8 bits. So in the LT Spice, I just tried this using C74HC85 magnitude comparator. I have used only 4 bits comparison. So I am giving the inputs A0, A1, A2, A3. Similarly, B0, B1, B2, B3. Okay. So I'll be getting 3 outputs, greater, equal, and lesser. I'm not giving anything to the cascading input. I'm just leaving it as such because see from less because see here in the truth table, if I'm using only one input up to this, I will be having only x don't care condition, so I have left as such. So this don't care conditions, if even though if I give or without giving, that doesn't make a problem. So 5 volt I am giving logical 5 volt. 5 volt means it is represents logic 1, 0 volt means logic 0. So 1100 1000. Okay, and if I run this, oh, I have to take spice directive. in the spice directive. I have to give dot lib space 74hc85 dot click OK. I'll place it here. Now run. You will be getting an error. View, see here, this is obviously a greater than b. Okay, so I will see only this gt alone. Add traces gt. Yeah, see this gt, you're getting 5. Logic 5 means 1. So if I'm adding another plot planes, add plot planes. So if I add lesser than, that should be 0. See 0 volt you're getting. And if you're adding greater, lesser, equal to should also give 0. Okay, so this is 0 volt, 0 volt, and this is 5 volt. Okay, this is 5 volt. So the background, okay, so if you see this, I can go ahead with that. Okay, this is your output. With this, I'll stop today for today's class. I'll just take the attendance.